Hello, and a warm welcome to everyone joining us today for the webinar GaN HEMT Technology from Epitaxy to Power Device Integration. I'll quickly introduce myself. I am Gunil, your host for today's session, and I'm from the marketing team here at Orbit and Skyline. Before we begin, I would request everyone to drop me a quick thumbs up in the chat box so that I know that I'm audible to all of you. All right. Thank you for your responses, everyone. Okay, before we begin, I would like to share a couple of webinar notes. Firstly, we'll be keeping your mics muted to avoid any disruptions. And second, I would request everyone to keep your cameras on so that we have a more engaging and connected session throughout. And third, drop your questions anytime in the chat box and we'll take them up during the Q&A round towards the end. Just in case, if we miss your question, feel free to drop your queries at hello@orbitskyline.com and we'll make sure that someone from our team gets back to you soon. So let's get started with today's webinar and welcome our speaker. So it's my pleasure to introduce everyone to Dr. Deepak Anandan. He is the process lead at Orbit and Skyline. And Deepak is a semiconductor process expert with over 10 years of hands-on cleanroom experiences of advanced 3.5 technologies. And he holds a PhD from the Compound Semiconductor Laboratory at NCTU Taiwan, where his research focused on 3.5 integration on silicon. At Orbit and Skyline, Deepak leads GaN epitaxy and process integration for power, HEMTs, and other advanced 3.5 devices, bridging research innovation with manufacturing scale implementation. So I would request that we can move on to the next slide. So before Deepak starts, here is a quick introduction about Orbit and Skyline for those who are hearing about us for the first time. Orbit and Skyline was established in 2009 and has over 15 years of experience in delivering comprehensive semiconductor solutions worldwide. We are a trusted partner for top-tier IC manufacturers and OEMs delivering comprehensive support across both CMOS and compound semiconductor fabrication environments. Orbit and Skyline proudly embodies the Make in India, Make for the World vision in the semiconductor domain and remains committed to the long-term growth of India's semiconductor capabilities. Guys, can you just hear me well? Please share your answers in the chat box. I'm waiting for everyone to reply. I just got a feedback that I'm not audible to a few people. Please confirm me on that. Audible clearly? All right. Thank you so much. Thank you, guys. Thank you for your responses. So yes, moving on to the next slide now. All right, so this is our clientele map. And as you can see that we have built strong partnerships with major fabs and OEMs across the globe. This global presence is a strong reflection of the trust we have built and the expertise we bring to the semiconductor ecosystem. So let's begin the session. Over to you, Dr. Deepak.
Thanks for the nice introduction, Gunil. And first of all, I would like to welcome you, all of you, for my session, which is basically going to be compound semiconductor device based. And I hope I'm audible to everyone.
Yes, Deepak, you're audible.
Okay, great. So yeah, this webinar is basically about the brief introduction about gallium nitride epitaxy as well as devices. And I hope a lot of other attendees are there who are more familiar about this topic already. But bear with me for a few of the basic things, and I also will touch upon few advanced technique as well. That would be interesting for you, I believe. So let's move into the outline. So if you look at the outline, so I divide the talk into 4 different sections. The first one starts with the market growth, and I will jump onto the epitaxy and the material pool which used for for the epitaxial technique. And then I will briefly explain the current techniques and types of devices which industry is following to develop the high power devices and how it can be replaceable for silicon based devices or silicon carbide. So I think most of you guys are well known about the compound semiconductor. It's basically a group 3 and group 5 material. So it may have a different material combinations, something like arsenide based as well as nitride based. So arsenide based, as you all know that those are highly useful for the laser technique, communication wave laser techniques, and some photodetector and with the current IoT techniques that can be potentially used. But if you move to the gallium nitride part, so the gallium nitride majorly playing role in 2 different main domains. One is optoelectronics, another one is electronics. If you dwell into electronic section, we can classify into 2 different sector. One is for power, another one is for RF devices. So let's focus on to the power devices first. Before dwell into the topic, I would like to cover the market growth and what is the status of gallium nitride when it compares to silicon carbide and silicon devices. So if you see the YOLE 2025 graph, so the prediction was almost 2 billion, if I'm not wrong. It's not clear for me. Wait. Yeah, it's around 355 million in 2024, which basically covers 7 different sectors. If you look closely, the major sector are consumer-based electronics and telecommunication-based electronics. Okay, so the prediction of CAGR in 2030, it will be almost like 3 billion, and 2034, it will turn it into 10 billion. That was the expectation from the market. And why it is more reliable right now in the market, why it is creating more demand, it is covering basically 2 different region. One is low and mid voltage, and the another one is overlap region. So low and mid voltage region, which is kind of domestic application or household applications, something like power adapters, chargers, and some other converters, which are potentially replacing the current silicon technology. So anything less than 900 volt, which is called as overlapping, more than 600 volt. So this is the most dominant domain right now in the high EV sector as well as PV inverter sector. Here we cannot say that which is the dominant factor, which is the dominant technology, because we have a competition of silicon carbide as well. Also gallium nitride, also we have a competition. So based on the application, based on the requirement, people are choosing either gallium nitride or silicon carbide. So we'll look into that, why particularly gallium nitride is important for the overlap region and mid voltage region. So if you see here, the gallium nitride, which gives very high switching speed compared to silicon and as well as silicon carbide. So it has a low switching loss and it operates at very high frequency. Like if you look into the silicon, anything less than 40 kilohertz is the operating frequency. If you go more than that, the switching losses will be very high. And also it delivers very high power density. Okay, so if you deeply dwell into the position of 650 volt device market, so comparing 3 different major technology, which is silicon based super junction MOSFET, that is also can be used from 500 to 1 kV, silicon carbide MOSFET, that is around more than 600 to several kVs, and gallium nitride, which is less than 650. So if you take this benchmark, the last 3 things like high switching speed, which is 65% less than the commercial silicon based MOSFET, because it has carrier, inversion, recovery phenomena, and these things potentially delays the switching operations. But when you compare to the gallium nitride, it doesn't have a minority carrier contributions. It just existing a channel. The channel either it can be depleted or it is turning on. So there is no minority carrier involvement here. So the switching speed will be very fast compared to silicon and silicon carbide. That's why it gives very high switching speed. So which is 65% less than current silicon technology. And also the HEMT structure typically gives the low conduction loss because it especially DMOD devices which is having very less R-on compared to silicon. So when the conduction loss is low, of course the frequency and the efficiency will be very high in the gallium nitride technology. That's why people are more concerned about the gallium nitride which is less than 650 volt, which could be the dominant device technology in the future. But of course, we cannot completely neglect that. Like there will be some other gate charges, parasitic inductors, and capacitance will be playing major role when we are developing the power MOSFET. Something like a field plate or gate capacitance. So those are inevitable parasitic capacitance, which always plays some role in the switching speed. So still it is matters, but however, compared to silicon technology, there is no minority carriers. So we get the win-win situation in the gallium nitride technology. So next, I would like to briefly give an introduction about the gallium nitride epitaxy, how it has been grown, and why you need a epitaxial technique, unlike silicon carbide or silicon, because you can make the device out of substrate itself. Okay, so here I would like to take three material as the comparison. Okay, the first one is silicon. When you look the silicon breakdown voltage on the electric field, especially electric field, it is like 10 times higher than the silicon. What does it mean actually? So if the electric field is more, critical electric field is more, then it can enhance the device R-on. It will significantly lower the R-on value of the HEMT. So the second thing is it can reduce the size of the devices. Like for example, if you are making 10 mm device of silicon based MOSFET, you can make the same performance device out of gallium nitride HEMT with 1 mm. So you can downscale the device size nearly 10 times. Okay, that's called Balgia's figure of merit. So which says that whenever you have a high critical electric field in the material, of course, it helps you to reduce the R-on nearly 10 times. And also, meanwhile, you can also increase the breakdown voltage of the device without compromising the device performance. If you look into the crystal structure, gallium nitride always exhibits the word-Z crystal structure, which is non-centrosymmetric. It means that in C-axis, there is no symmetric. It always have the disordered crystal structure. This disordered crystal structure, it is one of the key advantage why HEMT is playing major role because it contributes for the sheet carrier density at the 2D EG. But when you look into the substrate wise, we cannot grow like we don't have a bulk substrate, something like a 4-inch, 6-inch, or 8-inch gallium nitride substrate. It is very difficult to grow a big size substrate, unlike silicon and silicon carbide material. So that's why we always look for a epitaxial technique where you can integrate gallium nitride material on the foreign substrate, something like a sapphire, silicon carbide, or silicon. So if you look into the silicon, let me take the cursor. Pointer. Yeah. If you take the silicon has larger lattice constant compared to gallium nitride. So when you try to grow a gallium nitride on silicon, you have to stretch the gallium nitride to fit it with the silicon so that it forms the tensile strain. Okay. When you take the sapphire, the lattice constant of the sapphire will be lower compared to gallium nitride. So you need to compress the gallium nitride in order to fit with the substrate. So this is how basically the epitaxial technique will start. So anything above the critical thickness, the film will start to crack, then it will become a metamorphic. So if you grow a film before it is reaching the critical thickness, it becomes the pseudomorphic. Once it releases the strain in the lateral direction, then it will become a metamorphic. Of course, we need a metamorphic technique here because we need to have a multiple stack layers in order to elevate the strain in the buffer layer. So here are the three different substrate comparison. You can see that there are two different mismatches. One is thermal mismatch and another one is lattice mismatch. So if you take sapphire as an example, it has both lattice and thermal mismatch. It is playing huge role in the electronic section as well as photoelectronic sections. But however, if you integrate that on a sapphire substrate, due to lack of thermal expansion coefficient, it always exhibit a lot of dislocation density. But whereas if you take on silicon carbide, the lattice mismatch with respect to silicon carbide is very less when you compare with the silicon or aluminum oxide. It means sapphire. But other factor is, of course, silicon carbide is very good at thermal expansion coefficient. It dissipates the heat very fast compared to aluminum oxide substrate or silicon substrate. So in industry, most of the high frequency electronics, people would prefer to grow gallium nitride on silicon carbide substrate rather than the aluminum oxide substrate because of the huge lattice mismatch and thermal expansion coefficient. But when you look into the silicon technology, silicon is more abundant and well matured, and people are, foundry basis, they are doing work. So when you want to include this gallium nitride technology in the silicon fab, of course, it is an added advantage, right? So people are looking for the alternative whether we can grow gallium nitride on silicon so that they can increase the wafer size up to 6-inch and 12-inch. So in that case, of course, we need to mitigate the lattice mismatch effect and also thermal coefficient effect. You can see that the dislocation density is 1 order higher than compared to other two substrate. That is a one drawback. But if you consider the production yield wise and number of devices wise, then silicon is considered as one of the alternative, and you can increase the number of devices in a chip, which will eventually increase the throughput and the yield of the production. So as I mentioned, there is no ready-made gallium nitride wafer which is available in 4-inch or 6-inch size. That's why people are not going into the gallium nitride on growth on gallium nitride. But if you ask me, when you compare the silicon carbide device with the gallium nitride, it is really unfair comparison, I would say, because silicon carbide, you are making a substrate up to 6-inch to 8-inch. But when you look into the gallium nitride, you have to grow a epitaxial layer so that you can able to get the better performance. Until unless if there is a, if there is a proper way of comparison, you should have a gallium nitride substrate itself. But gallium nitride is a very forgiving material, and even though we have huge threading dislocation in the power of 7 to 8, still the gallium nitride able to give many good device performance. If you ask me, if the same level of threading dislocation, if you create any device out of gallium arsenide based material or indium arsenide based material, you would end up with nothing. There will not be any device performance. That's why gallium nitride is always a forgiving material. And I want to take silicon as a example here. Let's look into the buffer growth technique, because buffer is main layer which help us to accommodate the stress and strain and reduce the threading dislocation. And of course, whenever you are taking the silicon substrate, you must start with the aluminum nitride nucleation layer, because gallium direct deposition on silicon will intermix and it forms the rough surface and the crystal quality will be poor. In order to avoid that, we need to insert a thin layer of aluminum nitride nucleation layer. This aluminum nitride nucleation layer will not only help to accommodate the strain, but also it helps you to avoid the cracking and bowing, because the gallium nitride growth temperature is pretty high, anything above 1000 degrees Celsius. At that temperature, silicon substrate will start to bow, especially when you are dealing 4-inch or 6-inch or 8-inch substrate. Of course, the temperature uniformity and other stuffs will make silicon substrate to bow. So you will end up with the mole fraction, non-uniformity or thickness non-uniformity, many factors. So in order to avoid that, you need to insert the aluminum nitride nucleation layer. And after that, you will have a different kind of buffer growth technique. Industry will follow based on their technology. The first one is graded buffer. You can increase the gallium composition and reduce the aluminum composition from bottom to top, so that you will end up with the gallium nitride. This is called graded buffer. Like, there is no step graded buffer. It is linearly you are increasing the gallium composition and reducing the aluminum composition. So in that case, you will accompany the strain and also you mitigate the threading dislocation extension toward the active surface. And this is one technique. And the second technique is like you can grow a gallium nitride thick buffer layer, but you need to insert a thin layer of aluminum nitride in between. That help us to stop the stop the threading dislocation, which is probably extending to the top surface. And also it will act as a strain relief and a dislocation blocking layer, and it improves the quality a lot. If you take to the third one, so it is kind of superlattice. Superlattice is nothing but you are growing the thin layer of two different material alternatively. So if you grow that, it helps to bend the dislocation which is propagating onto the top surface, and also it improves the buffer resistivity. Buffer resistivity is quite important in order to avoid the buffer leakage, which leads to the breakdown the device. The fourth one is, unlike the first one, we are not linearly increasing the gallium composition. Here we are increasing step by step, like let's say 35% of aluminum gallium, 70% of gallium, then 90% of gallium, so that aluminum composition will be reduced if you take from bottom to top, and gallium composition will be increased. So it is pretty much easier compared to the linear one, because you will have the control over the aluminum and the gallium composition rate. So the respective TEM, you can see how the threading dislocations have been blocked with respect to different buffer technique. Okay, so you can see that the resistance of the buffer layer is quite important in order to avoid the leakage current through different channels, different layers. This is the leakage current path. The one you can see that it is going through the channel, that is main one. The second one is through the buffer layer, and another one is through the substrate interface. So there are a lot of leakage path, we could say that. And in order to avoid that, we need to implement a few more growth technique, something like we need to insert the back barrier, where the back barrier will have a larger band gap, which critically delay, it avoids the electron, accelerate and diffuse into the buffer layer, so that the leakage current and leaker current will be reduced, as well as the sheet carrier density will be preserved. That's a one method. The second method is like you need to dope the buffer layer with the help of carbon or iron. So basically this carbon and iron doping will act as a deep level acceptors, because these deep level acceptors are more important when you are growing high quality gallium nitride. The high quality gallium nitride basically naturally n-type. So when buffer has the n-type carrier, it has to be compensated and it should become highly resistive layer. So how to make that? You have to do the doping of carbon or iron so that it will attract the free carriers in the buffer layer. Then the buffer layer will become more resistive. And also you need to grow a thick buffer layer in order to increase the breakdown voltage. For example, if you are working on 200 volts devices, the volt buffer thickness should be around 2 to 2.5 micrometer. But if you are looking for a 650 volt or more than that, your buffer thickness should be as high as possible, like almost like 5 micrometer thickness, so that the vertical leakage current will be blocked, so that the breakdown voltage will be higher. You can see that the lateral leakage current and vertical leakage current of these devices. This paper actually published in our previous group. You can look into that using this link. So in order to grow the high quality gallium nitride, we always look for epitaxial technique, and mostly used industrial adapted growth technique is MOCVD, metal organic chemical vapor deposition, where it can go up to 1300 degrees Celsius. And the MOCVD usually comes with two different chamber design. One is vertical shower head, another one is a planetary design. So based on the application, people used to will opt for the options. And it also comes with the institute tools, something like Argus, and institute tools, something like APTT, which help us to measure the real-time temperature and the reflectance. And you can work on real-time basis where you can control the roughness, thickness, temperature variations. Everything can be controlled with the help of APTT reflectance. I would like to give a small explanation about how APTT institute measurements are working. If you take the left hand side image, this is basically a gallium nitride based nucleation layer along with a gallium nitride based buffer layer. So this is combination of nucleation layer and buffer layer. Okay, so the dotted line basically shows, one second, I will take it here. Yeah, the dotted line basically represent the temperature profile, and then a dark line represent the reflectance of the layer. Basically 363 nanometer laser will be used for the reflectance measurement. So here, initially the substrate reflectance will be measured. That's the first stage. The sapphire substrate reflectance will be around 1.7. And you need to grow with low temperature nucleation layer. So you have to control the thickness of the layer. So how do you control? Basically, people optimize that, okay, 2.5 times of initial reflectance. If it reaches, the nucleation layer thickness will be around 30 nanometer roughly. So once they grow and they stop the nucleation layer growth, and then they elevate the temperature from low temperature to high temperature in order to start the high temperature nucleation. So during that elevation, the low temperature gallium nitride will start to form a crystalline structure. It collides and it will form the highland. So once it start to form the island, the reflectance of the APTT will start to decrease. And after the third step, you need to increase the start supplying the gallium and nitride together in order to start the high temperature nucleation, high temperature buffer growth. When it starts, by the time when the highlands are spreaded across, it start to form the 2D growth instead of highland growth. So the collisions will try to cover the islands and make the thin film, start to form the thin film. When it start to form the thin film, the reflectance start to regain. So this is the basic phenomena, how you can interpret it, the epitaxial growth and the island formation, and where you need to stop, how the phenomena will be with respect to the reflectance and the growth, how it is converting from 2D to 3D or 3D to 2D. This kind of interpretation, you can get it from the in situ measurement technique. And one more finding is like when you have a high partial pressure of H2, which leads to rough nucleation layer, the rough nucleation layer is always better so that it can improve the quality of the buffer, which gives the high mobility, 2DEG mobility.
All right, guys. So there is a quick poll on your screens, and I would request everyone to quickly participate in this. And just let's wait for a couple of seconds and wait for all of your answers and see which option is getting the maximum votes here. We have received only 8 responses, guys. Be a little proactive and just open your chat box. Maybe it's there in your chat box also, if not on the screen. Okay, we have received 18 responses. And all right. So the question is, which company was the first to demonstrate 300 millimeter 12-inch GaN epitaxy on silicon in a scalable manufacturing environment? And most of you have answered option 4. And the second highest votes I can see is for TSMC. So guys, the answer for it is option number 4 only. So 50% of you have, called for the right answer. All right. Great. Thank you for your participation. Back to you, Deepak.
Thank you, Daniel. Thanks for the poll. Actually, yeah, Infineon recently demonstrated 12-inch epitaxial growth technique on silicon substrate. So that is the recent milestone company have ever achieved actually. So moving on to the devices, actually HEMT devices. The architecture of the HEMT device are pretty much same for gallium nitride power as well as gallium nitride RF. But only thing is, despite few modification in the gate structure and the drain to gate spacing, rest of the things are pretty much common. Because in gallium nitride RF devices, you don't need a very high breakdown voltage. You can just need nearly 60 volt or somewhere around 100 volt. But in case of gallium nitride power IMT, you need a breakdown voltage up to 650. That is the first level. The second level will be 900 volt. So based on that, people will design the buffer structure as well as the device architecture. So moving to the gallium nitride HEMT, the first gallium HEMT structure was designed on the gallium arsenide and aluminum gallium arsenide materials. So here gallium arsenide is a low band gap material, AlGas is the high band gap material. When you join these two heterojunction together, it forms the strading alignment. Okay, it's a type 1 band alignment. So when you have a high band gap material, the electrons which is close near to the barrier interface that try to jump over to the 2D and it forms the two-dimensional electron gas. Okay, that's called degenerator gas. The mobility of this two-dimensional gas will be very high. The electron will not flow into the Z direction. It only flows in the Y and X direction. Okay. And the second thing is, you will see that if the electrons are jumping to the 2D here the carriers will be depleted. It will become the space charge region. It means that the atoms are ionized. So when it start to ionize, these negative ions will try to repel the electrons which is presented in the 2D so that the mobility will be degrading. You don't need to lose this mobility. So people used to do two different things. One is they insert the spacer layer here, a thin spacer layer. Meanwhile, they control the doping here. It's called modulation doping. You need to define how far the doping concentration should be from the channel. So people used to go for two different technique. One is like a delta doping, yeah, high 2 to 3 nanometer of highly doped layer, which is around e power 20 to 21 highly doped layer. They will try to dope it in between the space, in between the barrier layer. So that what happens, the electron will start to jump, and of course the ionized atoms will be away from the channel so that they can have the very good mobility. That's the first case. But these all you need to have a one doping structures, doping barrier in order to provide the electrons to the channel. Where in case of gallium nitride, aluminum nitride, gallium nitride, you don't need any doping at all. We need to understand how the doping, without doping, how the carriers are coming to the 2DEG. Whereas in the gallium arsenide, aluminum gallium arsenide, if you increase the aluminum percentage more than 25 or 27, it creates the DX center, which will potentially act as a trapping center for the electrons. So that phenomena is not there in the gallium nitride. That is another advantage. Okay. And we also need to have one more barrier layer, which is typically aluminum nitride, not barrier layer, spacer layer, typically aluminum nitride, which help us to keep these charges fixed, ionized charges away from the 2DEG. So let's look into how the 2DEG is forming in the gallium nitride structures. Okay. So there is two different factor which contributes for the 2DEG formation. One is spontaneous polarization. Another one is piezoelectric polarization. Let's look into the spontaneous polarization. So this, let's say this is the substrate. Based on the nucleation layer, the gallium nitride either it end up with a nitride phase or gallium phase or nitride phase. So industry is mostly adopted the gallium phase rather than nitride phase because the growth is quite difficult for the N phase. Also, the growth window is very narrow. So let's look into the gallium phase. So as I mentioned, the gallium nitride is always exhibits the wurtzite crystal structure. So the wurtzite crystal structure, the A lattice constant is symmetric. But when you look into the C, it is a asymmetric actually. There is no inversion symmetry. It means that there is always displacement of atoms, so that it will always have some polarization between the atoms. The factor 2 is when you see the left hand side figure, consider this is gallium, and gallium has a 4 different nitrogen bondings. Okay, 4 atoms are bonded with the gallium. So when you have this kind of structure, the gallium nitride, the electron cloud distribution is not symmetric actually. So it is like nitride have a more electron cloud compared to the gallium. So what happens? There will be a electric dipole from positive to negative. The electric field forms in this direction. So the opposite to the electric field will be the polarization field. So each bonding will give some polarization field. So this is between the two different monolayers. When you add up as a complete layer, the net polarization across the z direction is not equal to 0. Let's look into this gallium phase. So the net polarization across this gallium nitride layer is almost 0.029 coulomb per meter square. This is the unit. Okay, so it's more like a negative on the surface, negative charge on the top surface, positive charge on the bottom surface. This is for the gallium nitride. When you try to integrate the aluminum nitride, the coulomb per meter square polarization is quite high compared to gallium nitride. That's why people are trying to integrate aluminum nitride as a barrier layer, where you will need only very thin aluminum nitride barrier layer. But the problem is aluminum nitride layer is a very large bandgap material. It is very hard to make the ohmic contact out of it, and the doping also very complex. So that is about the polarization. What is spontaneous polarization? So there are two factors. Okay, one is wurtzite disordered crystal structure. Another one is electron negativity between the gallium and nitride is different, so that it is forming the dipole, and it creates the polarization in some direction. Let's say top to bottom. So the third one is like second factor basically. You have to integrate the barrier layer here. Okay, so the barrier layer typically aluminum gallium nitride material. So aluminum gallium nitride material also will have a spontaneous polarization. Along with that, it also has the piezoelectric polarization because of tensile strain. I mentioned previously that when there is a lattice mismatch between two different material, when you try to grow on one on another, either it will form the tensile strain or compressive strain. So in the case of aluminum gallium nitride, it forms the tensile strain when you grow on the gallium nitride. So typically it gives the polarization again. On the top it is negative, here it is positive. And for gallium nitride, it is negative here and positive here. But here the net polarization field will be positive because the value of spontaneous polarization of aluminum gallium nitride, piezoelectric polarization of aluminum gallium nitride is much higher than compared to spontaneous polarization of gallium nitride here. So positive dominates here, which typically attracts the electron here, pulls the electron here. So basically what it does, the interface top surface will be having huge defect centers, something like unsaturated dangling bonds. Defect centers, those are having high electrons will be there in the top surface. So when you have the positive and negative polarization, the electric field will be in this direction. So electron always tend to follow opposite to the electric field. So the electrons at the interface will try to jump to the 2DEG so that it forms the two-dimensional electron gas at the interface. So in order to avoid that scattering, we will always go with the thin layer of spacer layer. So the previous structure basically a normally on device. It means that you have to apply negative bias in order to make it off. That's called depletion mode. Normally on devices. Okay. In order to make the device off normally, there is a technique which is called uh, normally off operation. So you have to integrate a P GaN layer on top of aluminum gallium layer so that this will act as a diode which repels the carriers at the interface so that there will not be any 2DEG which is lifted away from the Fermi level. So when there is no touch with the Fermi level, there is no 2DEG. So the device will act as a normally off device. So in order to make this normally on device into off device, we need to cascode the, we need to cascode the device with the silicon MOSFET. Yeah, let's go on.
Sorry to interrupt, Deepak. So we have one more poll, and I would request everyone to participate in this. How much of GaN technology can realistically be fabricated in CMOS silicon fab? So 40 to 70%, greater than 70%, less than 40%, 0% or not sure. So just quickly participate in this, guys. So far, we have received just 7 responses. Guys, please have a look in your chat box. I'll wait for a few seconds here. Okay, so 61% of you think that it's option B, and all right, so 21% think option A. So yeah, the correct answer is option B only. Deepak, would you like to add into this?
Yeah. So thank you, Gonil, for the post. So if you take the current CMOS technology, most of the device fabrication steps are pretty much equivalent to the silicon technology because it's a planarized structure. The only thing is in silicon fab, gold is prohibited because gold diffuse more into the silicon. So in order to avoid this gold intermix or contamination in the CMOS fab, you need to divide the line of metallization and other steps. Rest of the things, most of the 70% of process flow can be done in the existing CMOS fab itself. So right now, this is another current trend that companies try to utilize the CMOS fab for the gallium nitride technology as well. So moving on to that, I said that there is a two different type of devices, which is normally on and another one is normally off, right? So let's look into what are the device architecture which help us to achieve normally on and off, uh, characteristics. If you take the left-hand side figure, so this is basically a HEMT. It is nothing but metal, insulator, and a gate. Okay, metal, insulator, and gate, semiconductor. That's why it's called as HEMT. So basically, under the gate, there is no depletion of electrons. The channel always exists. You have to apply negative bias in order to make the device off. That's why we use silicon power devices, so that in cascade method, they can able to turn off the device. It means that gate always under some stress so that the device will remain off. Another technique in order to make the D mode to E mode, there are several methods. Among that, 4 I have taken. One is you need to integrate the P gallium nitride layer on that top of the gallium nitride HEMT structure. So what it does, basically it forms the diode, and due to that phase charge region, the beneath channel layer will be completely depleted and makes the device normally off. And there is no physical channel exist at the off condition. But the problem is the threshold voltage of this P GaN is very, very less. It's almost like a 1.7 volt. That's why, and also the doping in the P layer is very critical because of the activation energy of the magnesium in the P GaN layer is very high. So you need to have a separate annealing system in order to activate, and many other problems are existing along with the P GaN. And also the reliability issues also there. The second technique is like you need to recess little bit in the gallium nitride, aluminum gallium nitride barrier, and grow the high quality oxide layers. In that, you need to do the fluorine ion implantation. So the fluorine ion implantation, basically negative ion, which depletes the carriers beneath the channel. The third thing is partially recess gate with misempty. So it is also like a charge trapping layers are there that I will explain step by step. This is the most recent one, which my previous lab has demonstrated. They included the ferroelectric gate stack in order to have the positive VT around 4.7 to 5 volt. Okay, so if you take this structure, I'm going to discuss about this structure, integrating the P GaN layer on the top of HEMT structure so that it will help us to avoid the normally on condition and it turns off the device normally. Okay, so here two different constraints. One is you need to control the aluminum mole fraction as well as thickness of the barrier layer. If you miss the aluminum composition level, it will jump into the normally on because the 2DEG will go, I mean the conduction band will go below the Fermi level. If you look into the 10 nanometer aluminum gallium nitride with the mole fraction of 26, it is little above the Fermi level, so the device will be normally off. It means that whenever you have a lightly doped aluminum mole fraction with the combination of P GaN, it lifts the conduction band away from the Fermi level so that there is no 2DEG formation. And the problem here is you cannot, compromise more on the heat resistance. You can see that if you choose 1.7 as a threshold voltage, your sheet resistance keep on increases because the 2DEG sheet carrier density is very, very keep on decreasing when you are start to decreasing the thickness as well as aluminum composition. So it is one way or another. You have to either compensate the sheet resistance or you need to um, it's a trade-off. If you look for the low sheet resistance, your voltage threshold voltage will be very low. If you look for the low sheet resistance, threshold voltage will be very high. But you need to compensate. Like if the sheet resistance is high, the device performance will be low compared to D mode, normally on D mode. So let's look into the fluorine doped. As I said, it's a combination of recess plus miscemt. So in that case, they are implanting the fluorine ions at the gates junction, where the more fluorine ions will be incorporated inside, and the maximum intensity of fluorine ions will be at the interface exactly between the aluminum oxide and aluminum gallium nitride. But the problem is it try to diffuse into the channel where you will always have 1 e power 16 concentration. These fluorine ions will deplete the electrons as well, so which reduces the mobility. And also this is process complexity is more. Uh, and also yield will not be same as like every time when you are doing the same device, even though if it is optimized recipe, you will always have the deviation in the threshold voltage. And also when you operate the device at a high temperature, the fluorine ions will be ionized and will be energized, so that you will have the threshold voltage variations across the device with a different temperature. That's the main drawback of the fluorine ion dope. And another one is they are trying to include the multi-stack layer of charge traps, so that when you have controlled the negative charge here, it will help you to deplete the carriers here. But nevertheless, still it can help you to achieve very high current, and threshold voltage will be very low, significantly low. Still, this device needs extra cautions to make the device turn off completely, because it's a very tiny voltage. Even though for the small fluctuation it may have the chance that it will turn on and it will create the potential damage to the other circuits. So in order to avoid that, you need to have the some other passive circuits in order to make it device turn off always. This is the recent one I said, this is combination of gate recess plus ferroelectric stack. Here you will have the two different layer. One is aluminum oxide tunneling layer, and another one is capture layer, which help us to charge the storage structure. The charges will be taken from the 2DEG when you bias at 12 volt. Once it is biased, the charge remains here. And this negative charge will help you to deplete the carriers in the channel, so that it makes the device ideally off. The problem here is it's a ferroelectric. Whenever you are biasing, if you do the reverse, if you bring back the device to normal state, it will not follow the same line. It will always have the histories, and it will follow the previous voltage conditions. So it gives some kind of perplex situation here, that what is the current scenario, how this field of ferroelectric layers are reacting based on the small changes in the current voltage, and how fast it is reacting to the voltage variation. Those are limited actually. It is yet to be explored more. And of course, it is like ferroelectric layers are more degradable with respect to long lifetime. So it is kind of under the development stage. There is no prominent result, or industry is not adapted yet. So these are the VTH based alignment, where you can either make the device either turn normally on or normally off using different techniques, something like recess, fluorine ion implantation, PGAN incorporation. So these are the technique we use for the VT analysis, VT threshold voltage tuning process. If you look into the device aspect, how we can improve the breakdown voltage, because previously we studied about incorporating the back barrier and increasing the buffer thickness. It help you to achieve more breakdown voltage, right? So in device aspect also we have few, something like a field plate, which can be a source connected field plate or gate connected field plate, which helps to elevate the peak electric field at the gate junction. So what happens? The electric field will be very high at the gate interface towards the drift region. So this peak electric field is the main causes of breakdown earlier, so that you need to elevate it towards the drift region. So if you extend the field plate towards the drift region, this field will be distributed towards the drain, so that your breakdown voltage will increase. That's the first one. The second one is ideally you can design the gap between the gate and the drain so that this is the gap which crucially determines the breakdown voltage of the high power devices. The more distance you keep, the R-on will be high. So you need to have the trade-off. Like either if you are concerned about R-on, you should not concern about the breakdown voltage. And if you are concerned about the breakdown voltage, the distance should be long so that R-on will be low, high, very high. So it affects the device performance as well. And also you need to passivate the device in order to avoid the current collapse and also reduce the gate injection electrons which can be trapped here. Those kind of things will be avoided with the help of passivating with the silicon nitride. It can be done in situ or ex situ. Finally, the breakdown voltage can be improved with a thick buffer layer. And what else? Yeah. Also, for silicon case, the backside metal also will act as a field plate, which helps to elevate the peak electric field, and it improves the breakdown voltage. So from here, I can conclude that okay, we have gone through like what are the technique we use for threshold voltage modification as well as breakdown voltage in terms of epitaxial technique as well as device design. Yeah, thank you all. Thanks for the time.
Thank you so much, Deepak, for such an insightful session. So today's session offered a complete perspective on GaN HEMT technology and its role in modern power electronics. Now I would like to open the floor for your questions, and we'll take up a few questions now. And just in case we miss your question, you can anyways drop us an email at hello @orbitskyline.com, and we will get back to you soon. So, question number one is, can you explain in situ measurement um, more on how the experiment is carried out?
Okay. Okay. So in situ measurement, actually, we are using APTT, which is like the TT represent temperature and thickness. So we can able to measure the surface temperature rather than the thermocouple temperature. Basically, there is a difference between surface temperature and thermocouple temperature. The temperature variation will be high based on the set point. So here, in our gallium nitride system, we are using 633 laser, which actually can be sent inside the chamber, and it will be reflected in the substrate, and the reflected signal will be transferred to the analyzer spectrometer. Okay, so where you can able to see two different path signal. One is the reflection from the surface interface and the substrate, and another one is the top surface and the air layer. So there are two different interface where the path difference you can always calculate. So it can be either the signal can be added or subtracted so that you will have the oscillations. These oscillation help you to understand the thickness of the layer. If you ask me, if you want to understand more about this gallium nitride nucleation, maybe you can take the screenshot, and I can also even share a few more data on that. Basically, this reflectance, uh, this is the standard method they are using for the gallium nitride. First, they want to understand what is the initial reflectance of the substrate. Then, if it reaches 2.5 times of the intensity, they stop the growth at here so that the nucleation layer growth will be stopped. Then the temperature will be elevated to high temperature growth. During that time, the nucleation layer will form the 2D islands, so that reflectance start to decrease. And once you start the high temperature growth of gallium nitride, the 2D two-dimensional growth will start to form from the islands. So the collisions will happen more, and it start to form the islands, and the islands will be covered as a thin film. Then finally the overall thin film roughness and the coverage will be improved much as the growth prolongs. This is how they interpret it for the gallium nitride based. For aluminum nitride based, you don't need to use the same laser because it will be absorbed. So people will use 405 nanometer wavelength. And 950 nanometer wavelength typically used for surface temperature analysis, where you can help to identify the real surface temperature, not with respect to the thermocouple.
All right, thank you, Deepak, for answering. Hope your query is resolved now. Okay, so second question is how GaN will perform in terms of durability compared to others, and what about the wafer thickness?
So wafer thickness, basically it depends on the size of the wafer. Like if you are going for silicon, let's say silicon 6-inch, typically it will be 1 mm thickness. So if you are asking the thickness related analysis with respect to in situ measurement, then you need to feed the substrate thickness in the in situ measurement system, so that the tool will know that what is the thickness of the substrate. So wafer thickness is based on the size of the wafer. So for example, 2-inch sapphire, we always use 430 micrometer for 2-inch. And if you go more than that, like silicon, it will be around 375 nanometer. If you are going for silicon 111, it will be even thicker than 001. So typically in gallium arsenide system, we will not use 001. We will always use 111 to give the word structure. And if you ask me how gallium nitride will perform in terms of durability compared to others. Okay, the major problem with gallium nitride device is reliability issue, because as I mentioned earlier, still there are some investigation going on. What is the real source of electron for the 2D EG? So it means that there are a lot of defects that need to be addressed. It can be from buffer, it can be from barrier layer, it can be from surface. So here people are trying to control the VT variations and also breakdown voltage with respect to different technique like passivation, silicon nitride based passivation, or in situ based silicon nitride passivation. So still the reliability was the major concern in the gallium nitride. People are trying to address with the different passivation techniques.
Thank you, Deepak, for answering the question. We have one more question, and guys, just to wrap things up, I have also pinned up the email ID on which you can send your queries, because we are running short in time now. So the question, coming back to the question now, it is if we want to calibrate for gate leakage for p-GaN gated HEMT, then what are all the factors we need to think of?
Calibrate. No, there is no separate calibration technique you need to follow or factors. It's kind of what is the device requirement. For example, if you are really concerned about the 2D EG formation, or if you are really concerned about the threshold voltage, so both having the trade-off as I explained, right? So the gate leakage here, basically they are doing two different technique. One is Schottky contact. Another one is ohmic contact based. So here the gate reliability still remain questionable, because for example, for the Schottky contact, they always go with the nickel. So of course, whenever you are going for the Schottky contact, there will be always large leakage current because of tunneling of carriers, and the carriers will diffuse injected towards the drift region. So both the case, if you want to consider the gate leakage or suppress the gate leakage current, maybe you would good to go with optimizing the gallium nitride, metal structure on the p-GaN. That's a one thing. Second thing is you need to focus more on the surface passivation. Of course, surface passivation is pretty much same for D mode and the E mode. But in terms of gate structure, you need to have the more attention, because having the ohmic contact or having the Schottky contact on p-GaN material is quite difficult, because the carrier density will be considered as very low in the p-GaN, and you will not able to get the ohmic contact as good as like aluminum gallium nitride. That's one thing. Schottky can contact may be a good option, but still it has a leakage current.
All right, thank you, Deepak. And we'll take up the last question now. Which technology is currently leading to the low to mid power market as the best replacement for Si-based power transistors?
Right now, if you ask me, silicon is being a little bit away from the market, and gallium nitride is emerging. Right now, I would say most of the adapters, chargers have been replaced by the gallium nitride HEMT structures. But as you discussed, mid and low power, like there will always be a competition. Silicon carbide technology also, they want to bring it into the play, because it is also giving better performance compared to silicon. It's again based on the usage. For example, few devices, few tools, you should not have the electromagnetic interference. That electromagnetic interference will be very, very less when you take the gallium nitride devices. So it's again based on the applications. If you look into the application wise, then I would say gallium nitride is dominating compared to silicon carbide. Of course, the least one will be silicon.
Thank you, Deepak, for the detailed
Yeah.
explanations and for answering the audience's questions so clearly. So, lastly, on the closing notes, we'll be sending out a follow-up email shortly with a webinar recap video link and the slide deck so that you can catch up on anything that you have missed or you want to revisit. And once again, thank you, Deepak, for the enlightening session. And also, thank you to all our attendees for joining us today. We hope you found it valuable and we look forward to connecting with all of you again soon. Thank you, guys.
Thank you. Thank you for hosting the very good seminar. And also, I would like to thank the all participants. And I would be happy to answer your questions if you have any. Please collect my email address, and maybe we will keep in touch. Thank you.
Sure. I'll just add your email ID in the chat box as well for everyone.
Yeah, of course. Thank you.